Hopefully everybody can hear me. I think they can. Whole singer. How do I move this? Oh, just like that.
My computer was studying on Thursday. I feel like I couldn't get an A or B was my way.
Hey.
I'm trying to.
Okay, but still, either of those.
Lynn did on the other hand. I was
Okay, well, you took a victory, so.
yeah, that did take a
Okay.
So,
If everybody's good to start, I wanted to ask and do a little bit of an activity. If I want to see if anybody can tell me, not necessarily the like ins and outs, but at a high level, the three main things that get stepped through, the three like different communication tunnels that data flows through before it hits the network.
does it go through the router?
It does go through the router, Ben. That's the first one.
So from the computer to the network.
Yes. So the first one is the router. So when I send a message, where does that information go through? What channel does it go through before it hits the command port? So the first one is the router. So data immediately goes from the PC and it gets sent to the router. Okay, then we know where it goes to next. It's okay if you don't. I'm going to explain all of this. That's the first one it goes to.
So we're not talking specifically like the actual communication.
No, just like what objects it passes through.
You said it goes to the router first.
That's okay. The router modem, they are connected. For the sake of argument, they're the same thing. So this is pretty good.
Is it the Raspberry Pi?
It is not. It does not actually go through the Raspberry Pi. The Raspberry Pi is like the PC in this diagram.
What about, like, I'm saying Raspberry Pi connecting
It does, but that's more of like further down the send. I'm asking like if I'm sending a message from the Java software to talk to a meter, where does that data pass through in order to actually get information from the command port? No. So this is getting information from all this is really simple. Just like if I want to talk to a meter directly, I coded get mod config. I want to get the Wi-Fi, the like 1 or whatever. I send that command. What channels does that command go through as a like piece of information? Like as a bit stream, what channels does it go through? So it goes through the router. So your data is sent from a PC immediately goes to the router. The router figures out the IP address and the device that the message is trying to be sent to, which is the ESP8266, which I will expand upon what this is in the future. You starting to feel me, Ben? Trying to figure out what I'm doing?
Then it goes to the PIC.
Yes, then it goes to the PIC. I believe it's a PIC 32 FVKA, and I feel like such a big nerd for knowing that off the top of my head. That's also really bad handwriting. And then it goes to, from that, it goes to the other PIC on the command board. So these two things are what make up the Wi-Fi board. Those are the two major big players, right? So just for context, when we talk about talking to a meter from a piece of software, like Java software or from the website, the information, the wireless communication that's happening is happening between the PC, the router, and the ESP8266.
So the Wi-Fi is made of all three of those, or just the router?
So the Wi-Fi board itself is made of just the ESP8266 and the PIC. Yep. The wireless communication. Yeah.
Not ESP8266, that's the same as that.
I'll get to that. I'll explain what that is. That's on the Wi-Fi board. So the ESP8266 and the PIC, these make up the Wi-Fi board.
Is this different than when we were explaining the actual communication we're building, is that the same?
I think I'll explain. I think I'll answer that question. Yeah, so for the purposes of just wireless communication, so information gets sent from the PC, goes up to the router figures out the meter that has an IP address and MAC address, takes that message and points it to the device, to our meter, which is in this case, the ESP8266 is what is in charge of getting wireless packets from the router. That gets sent to the PIC that's on the Wi-Fi board, which then is going to talk to the command board. So that's the flow of communication. However, the PC router and ESP8266 are just the wireless portions of the communication. That's what we're going to talk about today. So I'm going to give you guys a background into just this offloader you're looking at now, of just networking basics. So there are 5 main layers to networking. What this is for those of you who are a little bit familiar with code, the same principle of having lower level stuff that is really, really simple, and then layers of abstraction above. So I have a definition slide next that's going to give little descriptions about all of it. The basic, yes. The basic thing to know is that the data link layer and the physical layer, they are the only hardware layers. So the network transport and application layer is all software. That's something really important to know. And usually the Mac and the PHY are built into one integrated chip. So that's something to know. The application layer, I'm going to go to the next slide a while because that's helps explain it. And I'm going to give you a sec to read it because there is a lot there. So the network layer is usually what is handled by the router. So that uses something called an IP table, which is just basically a map of computers' IP addresses and a way to get to them. So if one computer with one IP address sends a message, the router routes that information to another IP address and another destination. Does that make sense? So this is a lot. This is a whole lot of information to throw at you. The layers of internet, like there are whole graduate programs just in this. So like this is a whole field that you can go into. So I want to make sure that we get this at just a very high level understanding that the data link and the physical are the hardware components that determine your MAC address. But your network layer, which is determined by the router, controls things like your IP address. Very important distinction. The transport layer is now, so now we've established it has a unique identifier and it's on the network. The transport layer is how information gets sent back and forth using something, if I go to the previous slide, called TCP and UDP packets. Okay, so this is now, we have all the stuff, once we get to the network, or excuse me, once we get to the transport layer, we have all the information we need, like our unique identifier and our IP address on the router to participate in communication. Transport layer is where we start actually sending and receiving data from sources. And this is exactly the same with Ethernet as it is with Wi-Fi. The concept is exactly the same. The communication protocol is 100% entirely the same. The only difference is you use a wireless chip as your physical layer instead of an Ethernet chip. So instead of hardwiring it in, you have something that can talk wirelessly to a router. None of that affects coding because we code at the transport layer and up. So we don't have to worry about all of this stuff because it's super nice. So I'm going to go skip forward 2 slides and just talk about, yes?
Would it be fair to say that like, the physical layer is where the information itself is? Like if you're sending like 1s and 0s, and if it's like if you're sending data to, in our case, like the ESP8266 from the phone, does that enter in like the physical layer, or is that not what you're describing?
So this is all in terms of wireless networking. So information coming into the PHY would be coming in as network information. So there would be nothing coming in from the PIC.
Okay, so this isn't like the data itself enters at the bottom level.
So I think there's a clarification. Data does enter at the physical layer, but it just wouldn't be coming from the PIC in your case. It would be coming from a router.
Okay, so this is like reception.
This is reception, yeah. So your Mac and PHY chips basically convert the bitstream data, which I do have a slide on, the 1s and 0s that are going to be coming in from the router, and we'll be converting it into a readable format, such as I believe it's I2C. Yeah, so that's something to note. Is the PHY and the Mac do the conversion because this right here is a standard, and it is a broadband standard. So I don't know the exact frequencies, but you guys know radio, you can turn into a frequency in your car, you pick up a signal. Just like that, Wi-Fi is the very same concept. It's just a more advanced radio wave, and it's treated special. So you guys have heard of like 5G, you're sure all that, but the G just specifies the frequency in gigahertz. So 5G is just a 5 gigahertz radio frequency. It's all just frequencies. So that's something to just be really important, is that the reason that the bits can come in as high as low is because it's acting just like a higher frequency radio wave. And per the spec of like, this is what a Wi-Fi chip is, it has to be able to pick up frequencies on a specific radio wave. Does that make sense? Very, very high level. It's a whole lot more complicated than that. And to be honest with you, I don't fully understand it. A lot more complicated than that. But
the way it's actually like encoded onto a frequency is like, I have presentations on that.
Yes.
I need credit, but like, overall understood. Just
yes.
what we need to do is that it gets.
Yes, yes. And in terms of coding, and especially for what we do in the lab, we don't have to worry about any of that. So kind of zooming into what EMMS does is we use the chip called the ESP8266. I really should have brought a Wi-Fi board to show you guys to pass around, but I didn't. However, if you're watching this on Zoom, you probably have one next to you. This is a microcontroller with a built-in Wi-Fi functionality, which means that it has the ability to be a microcontroller to program. You can code Arduino on it if you really want to. And it also has pre-built functions at the transport layer. So what that means is we don't have to worry about sending how we're going to send all the data, converting it to ones and zeros. There's pre-built functions that are made by this manufacturer, pre-programmed into the chip using something called the AT Plus instruction set, which you guys don't need to worry about that for the purposes of this, because this is just on how wireless communication works and how we use it. What that means is that we pretty much tell this microcontroller using pre-built functions that are pre-made from the manufacturer. We say, hey, scan for Wi-Fi networks, pick this Wi-Fi network, connect to it, and now send and receive this data. So I'm going to talk about this a little bit more, but when devices connect to Wi-Fi, there's different kind of modes of operation that they can have at the transport layer. They can either be set up like a server, like how our website is set up, to just receive connections, or they can be set up like a sender to go out and get connections, or they can be both. But for the purposes of our meter, it makes the most sense to just have the meter be in something called a station mode, which means the meter is just kind of open, waiting to accept connections. So all you have to do is from a PC, say, hey, I'm going to send this message to this IP address of the meter, and it'll send that data, and the meter is just kind of already ready accepting all incoming connections on that network. Because that's a huge security risk of just be accepting all messages coming to it from the network, that's why we have two separate Wi-Fi networks. We have a closed-off network that just has the meters on it. So I'm just going to pause here. This is a lot. These slides are really dense. Everybody understanding what I mean. So transport layer, just to reiterate, is kind of like above IP addressing and MAC addressing and all that stuff. If anybody has clarifying on like MAC addresses and all that kind of craziness, I can explain that. But transport layer is basically now we want to send messages back and forth. Everything's set up, connected, we got all that. We want to actually send a TCP and UDP message. So, yes.
So like, are you saying that's not like entering like root tick or anything like that? I guess that's all past or
So this is just with wireless communication, or I should say like internet communication, because it works with hardwire too. So this isn't, so with the PIC, we're using communication protocols that you've heard like SPI, and like this is something totally different altogether. This is what we're talking about, like internet. So this is, what I'm teaching you guys right now is just kind of how the internet works, like how data in the internet is sent and received. So for getting it to the PIC, we will talk about that, because this microcontroller, like I said at the very beginning, it does give information to the PIC. And what it does, what its main purpose is to operate on the internet level on all these 5 main layers, get information being sent from a computer, and move that from internet language to SPI and send it over to the PIC. Because the PIC doesn't know how to read all the different layers and it's not set up to read internet traffic. Yeah, so what this is describing is data being sent from a PC to a router to the ESP8266. Does that make sense? Yeah, so all of that we're talking about now is just data coming in from a router, which is basically data coming in from the device. Yes, Ben?
So like the Wi-Fi board is cool, so like the ESP8266.
Yes.
It like knows what network it's on.
You have to program that in.
So that it says I'm on like the EMMS board Wi-Fi network.
Yes.
And it's accepting connections on that network.
On that LAN network. Yeah.
And it like has its own unique identifier, which is MAC address.
Which is the MAC layer.
And so other things that want to send something to it can scan the network for that address.
You don't need to scan the network. Yes, yes, what you're saying is.
And say, oh, that address is where I'm going to send
Yep.
X information.
Yep. Yep. And it sends it through something called TCP packets, which is just a really fancy way of specifying a certain pattern of bytes. Yeah. So that is an important clarification. Yes. Yes.
That's the between IP addresses and not like what's the difference?
Yeah. So an IP address, I want to, especially with the feedback that I've gotten from Tom, I'm careful not to get too complicated. So every device is unique that's on the internet, right? And so we have a metric ton of devices. So we need to make sure that they're right? So a MAC address is a hard-coded, static, meaning not changing, does not change value that is pre-programmed onto every single wireless device that's manufactured. That cannot be changed. So when we order ESP8266s, they come with built-in MAC addresses. Each one's different. They can't. Yeah, it's like with the law. Like you purchase MAC addresses from the IEEE company that's in charge of making standards. So if you build a device that can connect to the internet like this, you need to purchase, whenever you manufacture them and sell them, you need to purchase MAC addresses to put in them. Yeah. Yeah. So you buy them in batches. So a lot of our chips that we have, when you read all the MAC addresses, you can see the batches. You can see the patterns of that. What's up?
What's the manufacturing cheap?
Then the internet, I'm pretty sure it'll mess up communication between those computers. Because it'll either those connected devices. So I think it will either send double or no packets, or the router will kick them off the network. Who controls MAC addressing? IEEE, which is a government, I believe it's a government organization that controls. They're not government.
They're international.
They're international. They're the company. They're basically the people that control the standard. Yeah.
Would the difference between IP addresses and MAC addresses be like picture you've got a room of 100 people and you want to, like, all of them have their own name, their MAC address. Mm-hmm. But if you like just want to know them, like you want to count them off and say like, oh, send something to number 6, that would be like the IP address. Because the router doesn't care about its name. Or yeah.
Yeah, so
would that be a fair?
If you think about it, it might make sense thinking about it with the layers. So our MAC address is a hard-coded value, but the IP address is something that helps a router find a route from device to device.
So it makes a connection to that device and says, oh, that's connection number 4. Whenever I need to talk to this device, I use connection 4.
Yeah, so MAC address is just a value, it's just a number. It has no significance other than its unique identifier. An IP address is a physical path, or it's not a physical, I don't know enough to know if it's a physical path or not, but it is a path to the router to tell the router this is how I wirelessly communicate with this device. Does that make sense? To that IP address. So think of the IP address as it's like an address like a house, like I can drive to it, information can drive to it. But where a MAC address is just like the house number. Like if I tell you I live at 133 Hampton Drive, which is my home address, that's an address, right? Think about it as like, that's my MAC address. But my GPS directions to that address would be my IP address. Does that make sense?
So like computers, when you say like the IP address of like something is using like the lab to get to
Yeah, so it still is read. It's read by us as a number, but it's interpreted by the computer as like a path to get to it.
So does every individual like device have to because it's all?
When it's connected to a network, because that IP address changes,
Oh, you
So-
can,
and you can have multiple.
you can change.
And you can have multiple.
The MAC address cannot change the IP address.
Yes, and go ahead.
Like, can the IP, like, let's just say you're in a household and like many devices are connected to the same
Mhm.
Wi-Fi, so they would all have the same IP address.
They would all have different IP addresses. Because remember, it's GPS. I think it was like coordinates to go to different devices.
But
Oh,
it's
wait,
like,
so-
if it's in like the same house.
They'll have independent IP addresses and
Oh,
independent
really?
MAC. Yep.
So like we connect to the Wi-Fi, like, and like not
Every device connected to the site secure has its own IP address.
can you change that?
Mhm.
And then just when you reset the Wi-Fi connection.
Yes, that can happen.
Unless you said it's a step, you can make.
You can make them, yeah, for the purposes of what you're talking about, yes. And so you also have two different kinds of IP addresses. You have your local IP address, which is only talking to computers inside your Wi-Fi network. And then you have something called a public IP address, which has to do with the internet. Because it basically, so that public IP address changes, I think, either every time you load a web page or every time you open the browser for security. And in addition to that, that public IP address is hidden behind your router. So the information doesn't get sent directly to your computer, it gets sent to your router, and your router decrypts that IP address and sends it to that computer. No, do you need to explain what a router is?
Yeah,
Okay,
sorry.
you're completely okay.
You should draw some pictures.
Yeah, I'm trying to.
Draw some.
No, you're not dumb. You're not dumb. So Wi-Fi does not just come out of nowhere. It doesn't grow in the grass. You have something called a router, which pretty much just looks like a box with
It's
two.
like that box you have.
Yeah, which looks like two antennas sticking out of it.
It's like when they tell you to reset your Wi-Fi, you turn on, maybe.
Yes.
Maybe.
Yes. And
Yeah, okay.
So-
Wi-Fi doesn't grow on grass.
yes. So there, David pointed out earlier, there is a difference between a modem and a router. For the purposes of this presentation, we're just going to talk about router, and I'm going to say like one sentence about modems. So a computer, or an ESP8266, so I'm just going to say like personal computer. So this has a MAC address and a IP address, right? So once it's online, your local IP address, which is owned, so your router.
Sorry.
No, you're fine. It's making me think about how I've done this. So we're going to talk about a local network. So this is only IP addresses that are operating within one router talking to multiple devices.
Does a router have a specific network device?
Yes, you can change that. Yes.
Like in your house, like would that be a local one?
Mhm. Yep. So all of the devices that are, it's called local, like, because it's around you. So
And this is what we're using at TCP.
this is what we're teaching in TCZ. Yeah, I'm probably only going to talk about what we're doing in TCZ. So I'm just going to change this to meter, which is really just the chip. So it has a device. It has a MAC address and an IP address, right? MAC address is a unique identifier, doesn't change no matter where it's going. The IP address is a way for the router to know, hey, when information is being sent, this is where I put that information. So what the router is in charge of is receiving communication from all of the devices and sending out communication to all devices. It is the middleman. When you're talking to a device, like when we talked to a meter and you saw I had Eclipse pulled up and I was sending a message and your response back, it was being routed through the router. That's why the name is called a router, because it routes all the information through it. It's a hub of all of the wireless communication happening. You follow me?
So Zach is a device on that router, and so is the meter.
Yes.
He says, hey router, can you send this along to this dude?
Yep.
And it sends
It says sure.
to the computer. It comes from his computer to the router.
Yep.
To the
Do you
meter.
guys know like those old like telephone companies? You call the operator and they have a switch box and unplug you and plug you in.
Yeah.
A router is like a switch box. When it'll get calls saying, "Hey, I need to send an information here," and the router goes, "Okay," and lines it up and
Direct
Mhm. It routes it.
routes it.
Yeah, that's why it's called the router.
Router.
Yes. And if we have time left over, I can go more detail into this because there, again, networking is a whole.
Do you have a router?
No, a router is in charge of managing a wireless network.
So every wireless network is a router?
Yes, at least one.
So if you connect to a wireless network, you're going to a router?
Yes. Yep, connecting to a Wi-Fi network is connecting to a router. Yep. Yep. What's up, David? If you ask complicated questions, we're going to shut you down. Oh, I did say. So when we're talking about a router, we're talking about routing all of the information inside of a local Wi-Fi network like Messiah Secure. What a modem does is brings in an internet connection from an internet service provider and allows the router to talk to the internet. Connect to the rest of the world. So a lot of times a modem and a router will be built together. So when you like get Comcast internet and it's in that box, that is a router and a modem. What? Okay, well they can also be two separate boxes. Or so a modem unplugged operates as a router. Is that making sense to everybody? That does make a lot of sense. Okay, good. Rather than it is like communications is just a huge, just dense.
I'm 3,000 times smarter than I was when I walked in here. Because you explained what an IP address was, and before that I was like, it's a number.
And I knew that you specifically would want to know as in depth as possible what a TCP packet is and a UDP packet is, so I have a slide in it just for you. Before I advance to the next slide, I want to talk about the transport layer. So if I go, I apologize for skipping around. I did not think I would use this first slide as much. So
far we've been networking over.
Yes. Yep. So now we're talking about how the ESP uses the transport layer that we code at the transport layer. When we say send a message, we can specify if we want to send it TCP or UDP. The only difference, so also the only two ways that devices can send and receive information is TCP and UDP. All internet traffic is either TCP or UDP packets.
And we're not talking, again, nothing to do with like a security.
No, this is all wireless.
Like
So,
you literally don't need a wire connected.
you can. This is, yeah, I should say wireless is a bad description. This is internet. This is internet protocol. So it is in the same sense of like SPI where you connect wires and then they both know, okay, we operate an SPI protocol and like this is how we send data. Same kind of thing, but this is something new. So instead of SPI, this is TCP and UDP packets.
No.
Yes. Yep, so the internet spec of 802.11 says I connect these wires together and think about sending data in this way. And all devices that are using the internet have this pre-assumption. Does that make sense?
But with SPI, you have two things talking to each other. They're probably not going to change it, so you don't need like a super complex system to be able to like route everything together. But internet, like a larger network like this, you need a protocol that keeps track of everything and route all those connections together.
Yes.
So it's all communication. You could do either of them wirelessly
Or wired. Yep.
Can I ask a big question? You don't have to go depth right now, but like in general, like when you're saying like this is quote unquote internet, are you saying that like it's like access to like data? Like I guess I'm asking. That would internet really is? Or
you're saying like in the same sense.
So when we say after, and I'll
Okay,
explain.
sorry.
I'll explain in very general what the internet is.
okay.
So it's kind of just like a really big LAN network, but thinking about now we're at the transport layer. So all internet traffic being sent, whether wireless or wired, is TCP or UDP. I really, really apologize. I don't have definitions of TCP or UDP. I'm sure if I Google search to do it, that totally blanked when I was assembling this. Main difference, which I'm going to erase this to right, is that TCP uses something called error control. So when you see it, so TCP is I spelled guaranteed really wrong. It's probably still wrong.
It's actually a U with
No, it's PU.
It's not one.
It's PU.
Guarantee. Guarantee.
Yeah.
G-U-A-R.
G-U-A-R.
Think of like middle age spelling.
That?
No, it's not, that E you just wrote is
No.
no.
Guaranteed.
That's Now the news, I literally I need a. Do you want to see it? We're all set. That's
Now we know how to spell. That's the main goal of this presentation, so I know how to spell the word guarantees.
Just go.
Please tell me that's spelled correctly. Is that
That
wrong?
is correct.
Okay. So TCP is guaranteed to be correct. If you send it, so messages can be sent using the TCP protocol or the UDP protocol. Okay, so what that means is if I can send the same message through both kind of means. TCP means that the message has a whole bunch of error control on both ends to assure that during that wireless transmission or wired transmission, the data that's sent is the correct data received. It will either not work and say, hey, no data was sent, or it will work and the data on that other end is pretty much guaranteed to be correct. So exactly. So UDP is significantly faster, like greater than 2 times faster. However, there's no error control. So if something happens where it gets interference, too bad, so sad, you get that broken code. So where UDP is used is in streaming services, where you are streaming audio. So if you are streaming audio and you're at like 1600 kilobits per second, if one of those transmissions is messed up, you're not going to hear it. Does that make sense? What's up? Streaming a show, streaming audio, when you're sending data, you need to send data really fast. If, like, for instance, 1 pixel is off, your frames are so fast you're not going to notice that. So you care about speed more than just missing the occasional packet. That's also why, yeah, so everybody getting that. So TCP is more for like sending like data where it's important to send like really correct data, whether it's like configuration data or like information. And UDP is pretty much exclusively used for streaming. For 5 gigahertz and a lot of 2.4 gigahertz applications, you can get away with audio streaming on TCP, but not video. Video is pretty much predominantly done on UDP. Because video, like 4K video feed is a couple gigabytes per second, so you really need this.
So if I turn Netflix, that's what's streaming.
Yep, it's using UDP. Yep. Like I said, like this is like the lowest form of communication you can possibly send on the internet. Yeah, so it can't get any more simple. Does that make sense?
Yeah,
So you could send it more like with extra checks and stuff.
So for instance, a really high level way of sending and receiving information is clicking the download button on the website. Because that handles it all for you, it's all visual, it handles all the downloads, does all the initiation. The lowest level of downloading something would be like coding information using TCP and UDP packets to receive the bit stream of the data and processing it. Does that make sense?
all data.
All data, yep. So this is the
This is like key back instead of time.
this is the backest of the back end. Does not get any more back end than this. Where are you at? Yes, that I was just gonna flip to that slide. So this is an anatomy of a TCP packet. What's that? Ones and zeros. I don't want to go into this in too much detail because we really do not need to know this for EMMS, but it was specifically for Caitlin because I knew she was going to ask that question. So yes, because the TCP is as back end can get, it's just the ones and zeros. And same with the UDP packet. So so as you can see here, an IP header tells the router where the information is going to be sent to. Yes. Yep. And if there is a set limit to how much data can be sent per TCP packet, and so you can send multiple like chunks of information, like if you're downloading something extremely large, it'll be segmented into TCP packets and then they will be sent like in the linear fashion.
Does nothing
Yeah, so if you're downloading
Tyler change it?
Hmm? There's no compilers. This is a whole separate thing entirely. Yep.
So how do those zeros and ones?
They get processed through layer 1 and layer 2.
Which is the
So layer 2 is the max, so that's just kind of a number. But these bits enter the PHY, the physical layer, and that is what translates it from ones and zeros of a TCP packet to something more readable. So the PHY chip is like,
It's a chip.
yeah, well, to be completely honest with you, it's a part of a larger chip. It's a feature in a larger part of a chip. So the PHY is part of the ESP8266 microcontroller that is responsible for bringing in internet traffic and being readable by the microcontroller.
Okay.
Yes.
What exactly is that header? Is that just like, hey, I'm sending information number 1044?
Yeah, so if you're sending a whole bunch of information and it bits of TCP packets, it doesn't always send them from like 0 to 100. Sometimes it garbles them, or if it was pause in the middle and resume, sometimes the numbering gets off.
Or just like send different numbers and different sequences?
Yeah, so like sometimes it might send 3 then 4, but the router will receive 4 then 3 because of just interference and a whole bunch of other stuff. Yep. So the header is like an identifier, like, hey, this is like you have this large thing, we separate it into all these little chunks, send all the little chunks, and then the header is used for reassembly.
So it's just saying this is puzzle piece number.
Yep. Just like yep.
And because you have like this connection that's literally bouncing off walls.
Yep.
That is this way of putting it all back together.
Yeah. Or if we talk about hardwired, it's bouncing through a whole bunch of network switches, or hitting the router while the router's bogged down.
And it's assuming that it gets the entire segment together.
Yeah, so like say it's sending 1, 2, 3, 4, but there's a problem with number 3 and needs to do some extra error control, and now number 3 is coming in correctly while number 7 is coming in correctly. Does that make sense? Something like that, and that stuff does happen very frequently because when I first started coding this, I was like, oh, UDP will be faster. I like speed, and it was just a nightmare. So TCP is way, way better for this kind of stuff. It just hands it off for you. Yeah, when you're coding it, you can specify between TCP or UDP. So it's a TCP packet is basically the pattern of these bits.
So what is the actual
The pattern. So yes, because there is an identity. So because I don't understand, because I don't fully know the TCP packet pattern of how it sees data, of like what each chunk means. What I can tell you is that there is a piece in this information that tells the router that it is a TCP packet. That means the router has ability to know through a whole bunch of error control methods, which we're not going to go into today, to know whether or not the data being sent is correct or not. So it takes extra time. So there's an identifier in the sequence of 1s and 0s that tells the router it's a TCP packet, and the router will take extra care to make sure that that data is correct. A UDP packet is still 1s and 0s, but the pattern is different and designed for speed. So when the router receives it, it doesn't do any error control. It just pushes it on.
Is the router itself?
The router itself is this big.
It is.
It's
On the
yeah,
computer.
yeah. Yes. It actually is a computer. It runs Linux.
Is the header unique to TCP or does UDP also?
I'm assuming UDP has a header as well.
So it's still it's just like the either like number of times it sends it or
Yeah, like I said,
size of the packet or something.
the only main difference that we really need to care about between TCP and UDP is that TCP has error control, so it's guaranteed that the message you send is going to be received, whereas UDP is allowed for interference, but it's much faster.
Does it have like an ACNAC? Like does it send and if it doesn't get packet number 7, then it says, hey, I didn't get it?
That's TCP.
Okay, so
UDP does not give 2 flying parts. UDP is one way.
Okay.
It's just one way. You're sending data out there. You could be sending data to a computer that does not exist and you would never know it. Yep, just to be completely clear.
Or you can send it to a computer that does exist.
Yes, exactly. Like zip, absolutely zilch error control. You're just throwing stuff out there. So moving on to the next slide. So I touched on this before, but we are telling our chip that we want to be in something called a SIP server. So this is talking about when we enter this command, this is what the ESP8266 does. Yes? Microcontroller, yes. I'm using them interchangeably. Yeah. I will do my best to continue to use it microcontroller. It is, yeah, I can see how that. So the SIP server microcontroller basically is receiving commands, it's setting it up to receive commands. And we have it configured to just receive one connection at a time. So you can have just like a router or just like a normal computer, you can have multiple things connecting to it at the same time. But because we want simplicity and we only want to have one thing talking to it at the same time, we have it set up just to receive one connection at a time. So say two different devices are trying to send information to it, whichever one gets there first will be accepted, the second one will be blocked until it's done handling information from that first one. Does that make sense? The reason why we have to do this is because our specific microcontroller, which is not something for all wireless chips, okay, is this ESP8266 microcontroller can be used as a server mode or as a broadcasting a wireless IP address. So that chip that we have can become its own little router and broadcast its own little Wi-Fi network and have devices connect to it and forward and route information. Yep. So it's a pretty powerful little $1 machine.
Is the SIP server just can you describe what SIP server is in the whole thing?
Yeah, so SIP server obviously is a command you enter. It's a configuration option.
So you send this, like this is one of the things that we
send
the Arduino codes like through the Arduino to the ESP in setup.
So
this is like a programmable option.
Yes, this is a programmable option. We set this, we assume that there's nothing saved in memory. So the PIC, I can go into this more in depth later, but the PIC is controlling the ESP8266. This is kind of a little bit outside of what this lecture is on because it's just about wireless stuff and how we talk wirelessly. But essentially, the PIC executes this command to the ESP8266 every boot sequence. So whenever you turn it on, the PIC tells the ESP8266 like, hey, I don't know what you were doing before last time you were up, but I want to make sure that you are not broadcasting a Wi-Fi network. All you're going to do is connect to a preset one. Once you're connected, you're going to be a SIP server. Does that make sense?
Do you know if that means anything outside of the ESP?
Yeah, SIP server is unanimous. Like this, I didn't pull this from the manufacturer's website. This is just, this AT plus is actually a modem code. So it's used for like fax machines and stuff too.
So it's a widespread.
Yeah, it's a widespread use case, yeah. Yeah, and just to reiterate, data transfer, because the ESP8266 is just receiving stuff, data transfer is initiated by a PC, by something external. So it's just accepting any incoming connections. Yep. 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 So both of these sending and responses are TCP packets. So we're not talking about ports for the purposes of this this kind of workshop, but you would have to have a same port number. Yeah. So this is also assuming you're on the same wireless network. Yeah, and I'm gonna also I have screenshots, but if this can be Java software. This is just any. So for the purposes of EMMS, it's Java software, but this is really any device capable of sending a TCP packet. Does that make sense? So it's pretty much any device that can get the internet. And what I mean by that is any device that has like layer 1 and layer 2, a PHY and a MAC. And a PHY is like a legit thing. You can Google like PHY, and then you can buy like PHY chips. Yes.
The response back, is that like, hey meter, tell me how much power you're using, and that's the response back?
Yep.
Or is it like TCP backend stuff?
So TCP as a packet is back and forth, it's two-way. And that's part of the error control thing. But so this is going above, I guess this is going above layer 3 transport to layer 4 application.
Is that all happening like on the same line?
What do you mean? Yes, yes.
Okay.
Yep, yep.
It's all just going.
Well, yeah, this protocol operates on 8 wires, but for wireless communication, it's from the top. Yep. Yes. Yep. So it sends so a TCP packet, even though it is two-way, it is initiated by the Java software, and while the data is being sent over to the ESP8266 chip, it's two-way, just to make sure that the information being sent one way is received correctly. Does that make sense? And this is just how we are doing it. You can just send a TCP packet and be done with it. But because of the way that we have coded it, we send a command and the Wi-Fi module responds back. Does that make sense? So we have the ability. This is so how EMMS is working is we are opening a connection, right? So we're using TCP, we're opening a connection to send data, right? And then we are sending data this way. So this is now, we're going to the application layer. All right, so this is above transport. So this is how we're handling TCP packets. Does that make sense? And embedded in the TCP packets are the addresses of each device. It's like a envelope with addresses. So we are opening the connection, telling the router, hey, we want to talk. We are sending data, all right? And then per the protocol that we are using, so this is protocol now one level up, right? So this is like, how do you want to use TCP packets? Sending data, the ESP8266 has time to process it, time to get information is one thing. In the code, which I'm going to show on the next slide, is how we interpret the data. It comes in as like very readable things. There's nothing complicated in how we read it. And then the ESP8266, we keep the channel open. I know, so like that screenshot says, it's operating in station mode, so it receives connections. It does not make them, but once a connection is established, it can talk back. So it has done process and sends something back. So it did not initiate the initial connection, but it does send a message back. And then externally, actually either side's can close, but for EMMS, we close it on the Java software side. So it is incredibly confusing, and I do not like a lot do not understand. I'd rather be giving you a fraction of the information. Now this is like, so this would be like above transport layer. Yes. Yep, so each one of these things, like sending the command to open a connection is a TCP packet, or it's sent through TCP packets. Sending information is sent through TCP packets. Obviously the waiting time is just the processing. And then it receives it. So all of these things are done through the use of TCP packets. Follow me? There's like a level up. Different protocols, different everything, but it's a layer up. Now we're using what we just established. So what this means for us is we don't have to care about any of that when we're coding. We don't have to care about any of that. All of that I just showed you on all the other sides is just general knowledge to help you understand what's going on. General knowledge. What this means is you can literally just go, I want to communicate and send this message. That's literally it. You just have to specify the IP address of the meter, the port, and the message you want to send. It handles literally everything else. Yes?
How do we know what port?
Pre-turned port of port 80. We just arbitrarily pick one. Yep.
And then out of like year to two.
Yep. Also, port 80 you can look at on the website. Yes, David. This is one that was programmed by yours truly. However, I did it so that you guys don't have to. And in Java, you literally just have a command that's like, look for input, and it looks for input. So it was, it's really simple. It's called an input reader. Yep, client.communicate. So you send your message, and then the message returned from the meter is inputted into this variable, and then you can print the variable. It's just that easy. And so this is the PC computer side sending a message. From the meter side, also the C and the Java are the different languages. So we're doing the same thing, just in different languages. And when the response is received, rather than having a function that when it gets to it, it sends a message, this function is always looking for messages. So this is a very subtle difference, but it's important. And then this is like, okay, when we receive a command, how do we process it and send one back? So the sending back portion of the code I did not include, but just like Wi-Fi response check is a function, just Wi-Fi response send. Same thing. This is like crazy dense stuff. Yes, man.
Just really quick, you said 480 you can kept working.
Yeah.
Is that like only 480?
Mhm.
Just because 480 is 480.
Yep, port 80 has been deemed by IEEE to use the port for website traffic. Yep. Yeah, so in theory, you could send a, yeah, you have to code it, but in theory, you could receive stuff on a website and then display it.
So this isn't related to our internet system.
No, we just picked port 80 so that it's also guaranteed to be open. Certain ports require certain security privileges to send to. Port 80 is just a free open one. Yes.
So when you're sending like one like response,
Yes.
like back to simple things, those letters, essentially numbers, will get you like thousands of packets.
Yep. Yep. Exactly. You're exactly right. And all of that stuff is handled in pre-made functions by the manufacturer, so we don't have to do it.
So you're not like
We're not doing this. You just have to understand that this is just like what it's doing in the background.
you don't have to send a specific piece of packet that was open.
Nope.
Do you have to send it a thing to say, or is that baked into your like?
Baked into these codes.
So that whole thing is that command says open the connection, send this like all of these packets that have the information I want. Wait until you get a response, like get whatever you get back.
Yep. So there is something. So this is just kind of an aside, but so Microsoft is really the pioneer in this stuff, and so Microsoft computers, there's something called an end delimiter, which basically means that when the character, so we read it as the character \R. So that's a character turn character, right? \R. That's a character turn character. And this is, again, a character, so it's a sequence of zeros and ones. And when a computer receives this, so not in the TCP side, this is like, the data's been sent, we are interpreting the data. It is interpreted that when you receive this character, it's the end of a message. Yes, like a stop codon. But again, not operating on the TCP level, on the like a level up. What's up? Yep. Yep. They do. However, we're not talking about how computers interpret that. We're talking about wireless communication.
They combine it, but they're still separate characters.
They are still separate characters. However, for internet traffic, it is not combined. That is, you just use, just specifically \R for Microsoft. Yeah, if you send \end, it'll interpret it as 2 lines. Yes, yeah. So Microsoft is stupid and pretty much made it so no other computers are allowed to do this. So every other device that is not Microsoft sends a \R and a \n. And that is the stop codon.
Is that because Microsoft put like patented
Yep.
IP on
Yep.
it?
Yep. So Mac computers, Linux computers, Androids, all of it, which Android is Linux, but all of these use \R/n. So that is why when I'm coding and developing on my Windows computer, I have to do this, and then as soon as I finish it and put it on the Raspberry Pi, I have to make a code change to use this. Everywhere. It's super annoying, and that was part of what I forgot when I was trying to get it working earlier this cycle, because I just forgot about that. I was like, why isn't this working? So that again is all baked into these functions. So you guys don't have to worry about it. And I got so annoyed with it on the Java side, I put in it so it reads the operating system from the motherboard when you run the program. So I don't have to think about it anymore. Yeah. Yeah, so that is what says, hey, stop sending a packet. Or I'm sorry, that doesn't say stop sending a packet. Message. This is like when the meter side receives, the ESP receives this message, it closes the connection.
That's probably like the
Yes. So if you don't send that, you can keep this open and keep sending and receiving data. Does that make sense? We just have it coded that, well, we are using the default configuration that sending that closes it. Does that make sense? This is a lot. I'm hitting you with a heck of a lot of information. So
It's
this,
actually not sending the backslash anywhere.
Yeah.
It is sending like, that's just how they write it in code.
because it's a special character.
And you line character.
Yeah, this is called a character trying character. Yeah,
We can
so-
talk about that a bit more later.
Yeah, that's not worth running to. So that's all I got though. So that's everything. Thank you. So that is very, very strictly on just how we communicate wirelessly into the meter. That is not talking about what we do with the data when we get it, just Wi-Fi. And that was just a lot. My main goal of this lecture was to give you guys a huge background knowledge into like integrated communications networking. Yep.
Excellent. All right.